For centuries, we told ourselves a comforting story, that the universe had a slow, quiet childhood, lasting hundreds of millions of years. That was our foundation. But that story was wrong. A machine, 1.5 million kilometers away from us, looked 13.5 billion years into the past and found something there that was mathematically forbidden. Just 300 million years after the Big Bang, fully formed galaxies with billions of stars were already there. But the real crisis wasn't their existence, it was their violation of physics' timeline. If you are ready to see how our entire cosmic history must be rewritten, then leave us a like and subscribe to the channel. Because the rules of the universe have just changed forever. Let's begin. The scientific world believed in a story about the beginning of the universe. It was a story of a slow and patient start, a darkness lasting for hundreds of millions of years after the Big Bang, followed by the shy glow of the first stars. All our models, all our calculations pointed to this. But we were wrong, because a machine, launched on December 25, 2021, set out to burn these books. When the James Webb Space Telescope turned its eyes to the farthest point humanity had ever seen, it saw something that should not have been there. And in that moment, everything we thought we knew about the universe was shaken to its core. At the epicenter of this earthquake are structures called impossibly early galaxies. This name is not an exaggeration, because these galaxies defy the known laws of physics. According to our simulations, only gas clouds that had just begun to condense should have existed in the first 300 million years of the universe. Disorganized, small clusters of proto-galaxies, chaotic and primitive. However, when Webb looked right into this era, 13.5 billion years ago, it encountered a completely different landscape. Fully formed, bright, and massive galaxies stood before it. Some already hosted billions of stars. In a cosmic timeline, this was like finding a fully equipped skyscraper on a plot of land that should have been empty 6 months ago. Building a skyscraper takes years. It requires materials, labor, and a plan. So, it's impossible to build it below a certain amount of time. But there they were, these galaxies, existing right in that impossible time frame. The shock grew even bigger when astronomers calculated the mass of these objects. Some were so heavy that they seemed to contain more stellar mass than models allowed for all-star production in the universe at that time. The numbers simply didn't add up. So, how could scientists be so sure of what they were seeing? How can you determine the age of an object 13 billion light-years away? The answer lies in one of the most fundamental properties of the universe, its expansion. Webb uses this very feature to look back in time. In 1929, Edwin Hubble proved that galaxies are moving away from us, and the farther they are, the faster they recede. But this didn't mean that galaxies were flying through space like debris from an explosion. What was actually happening was much stranger, because it is not the galaxies themselves that are expanding, it is space itself. Think of dots on a balloon being inflated. As the balloon expands, the dots move away from each other not because they are moving on the surface, but because the surface itself is growing. Just like this, galaxies are carried along by this expansion of space. This expansion physically stretches everything within it, including light. The wavelength of light determines its color. Blue light has a short wavelength, red light has a long one. A beam of blue light that left a young galaxy 13.5 billion years ago gets stretched so much by the expansion of space on its way to us that its wavelength shifts to red, or even to infrared light, that we cannot see with our eyes. Astronomers call this redshift. By measuring a galaxy's redshift, they can precisely calculate how far away it is and how long its light has been traveling. An object with a redshift value of 13 means we are seeing it as it was when the universe was only a few hundred million years old. This is why Webb is a time machine. But this time machine didn't just reveal that these galaxies were very large. It exposed a deeper problem with the very matter that formed them. The existence of these impossible galaxies was a shock, but their chemistry was just as impossible. One of Webb's most powerful tools is the spectrograph. This device breaks down the light from a galaxy into its components, just as a prism separates sunlight into a rainbow. Every chemical element in the universe leaves its own unique signature in the light spectrum. Oxygen's fingerprint is different. carbon's is different, and iron's is completely different. By reading these signatures, scientists can know what a galaxy 13 billion light-years away is made of without ever going there. However, after the Big Bang, there were only 3 elements in the universe: hydrogen, helium, and a very small amount of lithium. Heavier elements like carbon, oxygen, and iron are produced inside stars. When giant stars live and die, exploding as supernovae, they scatter these heavy elements into space. So, for a galaxy to have heavy elements, at least one generation of giant stars must have been born, lived, and died. This cycle takes at least 10 million years. But Webb found traces of oxygen, carbon, and iron in galaxies that were only 300 to 500 million years old. This meant these galaxies had already consumed at least one stellar generation, and this was happening in an era when models predicted the first star was just beginning to shine. In some galaxies, the enrichment rate was so high that a single generation was not enough. It was as if multiple cycles had already occurred. This was a situation where time itself was insufficient. ESO. We have galaxies that formed much earlier than they should have. They are much larger and more massive than models allow, and they have a much richer chemistry than physics permits. Each of these discoveries alone would have been a sensation. But when they all come together, they paint a picture of a universe that lived its childhood at an incomprehensible speed. The timeline was broken. The math didn't add up. Our most fundamental models for the formation of structures in the cosmos were inadequate. The universe was running a marathon when it had just started to crawl. This situation forced scientists to ask a much more fundamental question. If everything happened so fast, what engine was driving this process? And the answer to that question was not a single engine, but a mysterious process operating on 2 fronts at once. Because this was not just a problem of galaxies, but also of the monsters hiding in the centers of these galaxies, the most gluttonous inhabitants of the universe, supermassive black holes. For the problem with these early galaxies was not just the mass of their stars, but also the black holes lurking in their centers, which had grown at an unbelievable rate. Normally, a black hole is formed from the death of a giant star. It begins its life with a mass only a few tens of times that of the Sun. Then it slowly grows by swallowing surrounding gas and merging with other black holes. This is a patient process that takes billions of years. Sagittarius A star, the black hole at the center of our own galaxy, is a perfect example. Its mass is about 4 million times that of the Sun, but it has taken almost the entire lifetime of the universe to reach this size. But when Webb looked into periods when the universe was not even 1 billion years old, it found quasars powered by black holes with masses of 100 million, or even 1 billion times that of the million. Sunday. This was like a newborn baby having the mass of an adult. The timeline was completely wrong. These monsters reached the mass our galaxy's black hole achieved in a lifetime, in less than a 14th of the total age of the universe. ESO. How is this physically possible? Isn't there a limit to how fast a black hole can grow? Yes, there is. There is a physical limit to how fast a black hole can accrete matter. It's called the Eddington limit. Imagine trying to drink water from a fire hose running at full power. The pressure of the water would push you back before you could swallow. The situation is similar for a black hole. If it feeds too greedily, the matter falling into it heats up so much that it radiates an enormous amount of energy. This energy creates an outward pressure, pushing away the incoming gas, its own food. This is a natural braking system that prevents a black hole from running out of control. However, these first monsters seem to have never used this brake. But that wasn't even the solution to the puzzle. Because even if they fed continuously at the absolute limit, it was mathematically impossible for them to grow from a stellar mass seed to these colossal sizes. There simply wasn't enough time. ESO scientists understood. If the growth process followed the rules, then the seeds themselves must be wrong. This impossible growth puzzle prompted some theorists to propose a radical solution: direct collapse black holes. This theory completely bypasses the standard story of black hole formation. Normally, a gas cloud collapses and forms hundreds or thousands of stars. Some of these stars die and leave small black hole seeds of a few tens of solar masses. But, according to this theory, under the special conditions of the early universe, a giant gas cloud could completely skip the star formation stage, because these primordial clouds lacked the heavy elements that allow for cooling and fragmentation. So, the cloud could not break up into many small stars, but instead would collapse in on itself as a single unit, a whole. Imagine a giant gas cloud, with a mass of 100,000 or perhaps even 1,000,000 times that of the Sun, collapsing directly into a single black hole. This was like carving a skyscraper out of a ready-made mountain, instead of building it brick by brick. This process could create a seed with an initial mass of 100,000 solar masses, instead of a seed of a few tens of solar masses. If you start with such a large seed, reaching billions of solar masses in a few 100 million years, even by feeding at the Eddington limit, suddenly becomes mathematically possible. If this theory is correct, the ancestors of today's giants were not dead stars, but these ancient gas clouds that turned directly into black holes. So, we have theories, impossible galaxies that are too early, too large, and too element-rich. And at their centers, impossible black holes that require a completely new origin story to explain their existence. These models, these problems, they all made sense on paper, but these were hypotheses put forward to explain strange data. What was the telescope itself seeing? What exactly were the observations that put the scientific world on a state of quiet alert? Why did that first image, presented to the public on July 11th, 2022, create a shockwave? Because hidden in the pixels of that image was the evidence that would rewrite the textbooks. And that day came, July 11th, 2022. A press conference was held at the White House, and an image was released. The image was beautiful. It was breathtaking. However, in research groups around the world, the same image caused a quiet alarm, because before Webb was launched, astronomers had prepared detailed computer simulations of what the early universe should look like. These simulations had been tested for decades with Hubble data, refined and classified as reliable. But Webb's first deep field image simply did not fit. The first impossibility was immediately apparent. In the pixels of this image, there were galaxies that should not have been there. One research group described their findings as galaxies with masses that challenged our standard models. Another found objects that, if confirmed, contained more stellar mass than simulations had allowed for the entire early universe up to that point. They were too bright. They were too orderly. They were far, far too large for the age attributed to them by their redshift measurements. Astronomers began to give these objects a name: impossible early galaxies. And as more data came in, these impossibilities began to accumulate. Galaxies with redshifts of 8, 10, 12, even 13 emerged. Each was more massive than the models allowed. Each carried chemical signatures that required generations of stellar life and death to produce. The textbooks were beginning to burn. Then, in mid-2023, a team published results on 6 candidate galaxies. All were in that extremely early time frame, just 500 to 700 million years after the Big Bang. Each of these galaxies appeared to contain between 10 billion and 100 billion times the stellar mass of our Sunday. These numbers didn't add up. It was like finding a fully equipped skyscraper on a plot of land that was empty 6 months ago. Building a skyscraper requires years of planning, permits, materials, and labor. You cannot rush it below a certain threshold, but Webb's galaxies had done just that. They had built themselves in a much shorter time than the universe had allowed them. The standard models of cosmology, Lambda-CDM, began to crack under the pressure of these observations. However, the biggest shock came from a single galaxy, an object nicknamed Maisie's Galaxy among researchers. The team found it in the first deep field images. Its redshift placed it at about 390 million years after the Big Bang. It was extremely early. It contained billions of stars. It was dense and bright. But when scientists made their mass estimates, they found more stellar material than models predicted for that region of the early universe. How could this be possible? A galaxy cannot be heavier than all the raw material in its surroundings. This was a violation of the laws of physics. This galaxy, if it was this massive, must have formed its stars at such a frantic rate that it would have completely consumed its surrounding gas in just a few million years. Today's galaxies, even the most active ones, form stars at a tiny fraction of this rate. There wasn't enough time, there wasn't enough material, but the galaxy was there. And just when scientists thought it couldn't get any stranger, a ghost appeared, a galaxy that had existed for decades as a blank spot in telescope data. Astronomers pointed Hubble to its coordinates. They saw empty space. They looked with other ground-based telescopes. Again, nothing. That region seemed completely empty. But they were wrong, because in that void, there was a dense, active galaxy, producing stars 1,000 times faster than the Milky Way does today. Its name was Aztef 71. It was just hidden behind such a thick curtain of cosmic dust that not a single photon of visible light could escape. Dust absorbs the visible and ultraviolet light from young stars like a sponge, and then re-emits that energy as infrared light. Hubble's eyes were blind to this infrared light. However, when the James Webb Space Telescope pointed its infrared cameras to the same coordinates in late 2023, that blank spot disappeared. In its place came a bright, clearly defined source of infrared emission. SO. We have galaxies that are too large. We have galaxies that mature too early. We have galaxies that contain more material than their surroundings can provide. And we learned that we have been systematically overlooking the most active galaxies because they were hidden behind curtains of dust. Each of these discoveries was a nail in the coffin of the old model, but they all raised the same, much deeper question. If structures formed so quickly, what force was driving them? And where did all that heavy matter come from so early in the universe? So, scientists decided to look deeper into the moments of death in the universe, because the death of stars is the key to understanding the life of the universe. And on March 14th, 2025, a gamma ray burst passed through the solar system. These bursts are the most energetic events in the universe. In a fraction of a second, a single burst can release more energy than the sun will emit in its entire 10 billion year lifetime. But this burst was different. Its source was unusual. When the calculations were done, the burst, designated GRB 250314a, was found to have a redshift of 7.3. This meant the explosion occurred when the universe was only 700 million years old. Its light had taken over 13 billion years to reach us. These types of bursts are caused by the death of a giant star. When a star tens of times more massive than the Sun exhausts its fuel, its core collapses into a black hole, and two jets of energy erupt from its poles at nearly the speed of light. If one of these jets is pointed directly at Earth, we see it as a gamma ray burst. Scientists pointed Webb at the fading afterglow of the burst and did something extraordinary. They compared the chemical signature of this ancient explosion with supernovae observed in the modern universe in galaxies right next to us. The result was shocking. The match was almost perfect. This should not have happened. Because scientists expected that stars formed in primordial environments with almost no heavy elements would die in different ways than the well-studied deaths of modern stars. But the data from GRB 250314 showed a collapse and explosion consistent with supernovae in nearby galaxies that had evolved for billions of years longer. Over 13 billion years of cosmic history, the way a star dies had not changed. The physics was the same, but this continuity deepened another puzzle, because if the mechanism of stellar death was always the same, then the black hole seeds emerging from the deaths of the first stars should also have been of modest size. The collapse of a star leaves a black hole roughly proportional to its own mass. A 30 solar mass star might leave a black hole of 5 to 10 solar masses, but we had already seen that Webb found quasars powered by supermassive black holes of hundreds of millions, or even a billion solar masses, within the first billion years of the universe. The consistency in how stars die did not solve the mystery of where these giant black holes came from. On the contrary, it deepened it. The standard model had no answer. So, some researchers turned to a radical idea, a type of star the universe should never have produced. These objects are called dark stars, and they are unlike anything we know. A normal star shines through nuclear fusion in its core. It produces energy by converting hydrogen into helium. But a dark star gets its energy from a completely different and invisible source: dark matter. According to theoretical frameworks, when a dark matter particle and its antiparticle meet, they annihilate each other. This annihilation releases a tremendous amount of energy. In the early universe, the density of dark matter was much higher than it is today. According to theorists, this annihilation process could have become an energy source within a collapsing gas cloud before hydrogen fusion could begin. The result would be a bloated, hot, and bright object, sustained not by hydrogen fusion but by the annihilation of dark matter. Models suggest these stars could reach masses of 100,000, or even 1,000,000 times that of the Sunday. A single dark star could produce more light than most modern galaxies. Alone, it could emit more energy than all of the 200 to 400 billion stars in the Milky Way combined. But the most crucial part is this. If these dark stars existed, at the end of their lives, they could collapse directly, leaving behind giant black hole seeds of hundreds of thousands of solar masses. This could solve the puzzle of how early supermassive black holes grew so quickly in one fell swoop. When scientists re-examined Webb's data, they noticed that some bright and mysterious objects matched the predicted spectral signature of a dark star better than any galaxy model. All these discoveries, from impossible galaxies to consistent star deaths and theoretical dark stars, raise a fundamental question. How does the telescope itself work? What allows it to see these impossible structures, these ancient explosions, and these potential monsters? The answer is simple and at the same time extremely difficult. Cold. A coldness near absolute zero. Because to see all this, the machine itself must be quieter than even the faintest whisper of the universe. Also, how does such a sensitive machine achieve this? But how does it work? How can such a sensitive machine hear the faintest whispers of the universe that set out 13.5 billion years ago? Let's slow down our tempo a bit now and look at the technique itself. Because the telescope's success is not magic, it is the result of a series of ingenious engineering feats, all based on one fundamental principle: escaping heat. Because Webb does not see the universe as we see it. It sees the universe in infrared light, which is essentially heat radiation, SO. Even the slightest heat emission from the telescope itself would completely overwhelm the signals it is trying to detect. The first and most radical solution to this problem was to take the telescope as far away as possible from the biggest heat source in our neighborhood, Earth itself. If Webb were in a low Earth orbit like the Hubble telescope, just 550 kilometers above us, it would be completely blinded by the heat reflected and emitted from our planet. This would be like trying to see the flicker of a candle a kilometer away while someone shines a spotlight in your face. That's why Webb is located at a very special point in space, 1.5 million kilometers from Earth. This point is called the second Lagrange point, or LU2. This is not a random place. It is a magical point where the gravitational forces of the Earth and the Sun are perfectly balanced. Imagine a small marble standing exactly between two large magnets pulling in opposite directions. The marble remains stable and relatively motionless there. Webb does exactly that. Anchored at this point, it orbits the Sun along with the Earth, looking into the depths of the universe. This distance is immense. Astronauts could go to Hubble to repair and upgrade it. Webb is completely on its own. This is a one-way mission. Any mistake would be the end. But even a distance of 1.5 million kilometers was not enough, because the Sun was still there, a huge and relentless source of heat. So engineers gave Webb a shield. But this is no ordinary shield. It is one of the most remarkable engineering feats ever constructed. It is the size of a tennis court and consists of 5 separate layers. Each of these layers is thinner than a human fingernail. It is made of a special material called kapton, coated with aluminum and silicon to reflect heat with extreme efficiency. But the real genius is not in the layers themselves, but in the space between them, because the 5 layers do not touch. There are precisely calculated vacuum gaps between them. This design is crucial, as it prevents heat from passing from one layer to another through conduction, like heat spreading through a metal spoon in a hot cup of coffee. Instead, heat can only travel through radiation, and each layer reflects most of this radiation back into space. The result is a mind-boggling temperature difference. On the sun-facing side of the shield, the temperature reaches a scorching 110 degrees Celsius. But on the shaded side, where the telescope's sensitive optics are located, the temperature drops to a freezing -233 degrees Celsius. This huge temperature difference of more than 340 degrees exists on a structure thinner than the lid of a laptop. The deployment of this shield, which was folded like complex origami, was one of the most terrifying moments of the mission. Hundreds of pins, cables, and latches had to be released in a perfect sequence. A single mistake could have instantly ended the $10 billion mission. But everything worked perfectly. Now that the telescope was in a cold place and protected by a perfect shield, it was time to open its eye. And what an eye! Webb's primary mirror is not a single piece of glass. This would have been impossible due to both weight and the folding requirements during launch. Instead, the mirror consists of 18 separate hexagonal segments that look like a giant golden honeycomb. Each of these segments is made of an ultralight and durable metal called beryllium. Beryllium was chosen because, unlike many other materials, it remains exceptionally stable in the extreme cold of space without cracking or deforming. But the real secret is not in the beryllium itself, but in its coating. Each segment is coated with a microscopically thin layer of pure gold. Why gold? Because gold reflects infrared light better than almost any other metal. This is crucial for capturing even the faintest photons that have traveled for 13.5 billion years across the expanding universe. The diameter of this giant mirror is 6.5 meters. This is almost 3 times wider than Hubble's 2.5 meter mirror. This larger area means Webb can collect about 7 times more light than Hubble. It's like your pupils dilating in a dark room. The more light you collect, the fainter and more distant objects you can see. But for these 18 segments to function as a single mirror, they had to be aligned with incredible precision, to an accuracy of a fraction of the width of a human hair. This weeks-long process was carried out with tiny robotic motors in space, until all 18 segments worked together as a single, perfect surface. SO, we have a telescope hiding from the heat of the Earth and Sunday. We have a giant gold-coated mirror designed to capture the faintest infrared light from the most distant corners of the cosmos. All these engineering achievements are designed to perform a single task, to collect photons. But just collecting light is not enough. You also need to be able to read the secrets hidden within that light. And this is where the telescope's real detectives, its scientific instruments, come into play. So, how do they work? And this is where they come in. Because Webb has not just one, but several different eyes that serve as its scientific instruments. Each is designed to see a different part of the infrared spectrum and to answer a different kind of question. The first and perhaps most important of these instruments is the spectrograph. If you want to understand it, you should think of it not as a camera, but as a cosmic fingerprint reader. It transforms light into pure information. When a beam of light from a galaxy 13 billion light-years away enters a spectrograph, the instrument does something remarkable. It splits this single beam of light into all its component colors, just as a prism separates white sunlight into a rainbow. But in this cosmic rainbow, the spectrum, dark or bright lines appear. These lines are like the unique ridges in a human fingerprint. Every chemical element in the universe, from hydrogen to iron, absorbs and emits light at very specific, unique wavelengths. Oxygen leaves a different trace than carbon, and iron leaves a completely different signature. By reading these traces, scientists can tell with absolute certainty what a distant galaxy is made of. They can determine its temperature, its density, and even its movements. This is an incredibly powerful capability. This is why the discovery of heavy elements in the first galaxies was so alarming. It was not a guess. It was concrete, chemical evidence read directly from the fingerprints in the light. Without the spectrograph, we would only see bright blobs. Thanks to it, we saw evidence of an impossible chemical history. The standard model predicted the fingerprints should be simple, just hydrogen and helium. But the spectrograph showed complex, mature fingerprints that told a whole story of stellar life and death, at a time when that history should not have been written yet. But Webb doesn't just read the composition of light. It has different eyes to see different kinds of light. Imagine being able to see a scene simultaneously with both normal eyes and a military night vision goggle. Both show you the same scene, but completely different details emerge. Webb does exactly this with its main cameras, NIRCam and MIRI. The near-infrared camera, NIRCam, is Webb's primary eye. It sees a range from the reddest light Hubble could see to wavelengths invisible to the human eye. This is the perfect range to capture the starlight of the most distant galaxies, which has been extremely stretched by cosmic redshift. When Webb finds a new record-breaking galaxy, it is usually NARCam that sees it first. But Webb has another special instrument called MIRI, the mid-infrared instrument, and this instrument sees a completely different universe. MIRI looks at even longer wavelengths, at colder heat radiation. This allows it to do something NIRCam cannot: penetrate into the dense, cold dust clouds where star formation is taking place. While NIRCam shows a galaxy's existing stars, MIRI shows the dust and gas in the same galaxy, the raw material from which new stars are just forming. When you combine these two images, you get a complete portrait of a galaxy. But for MIRI to work, it needs to be incredibly cold. To prevent its own heat from overwhelming the faint signals it's trying to detect, it must be cooled to just 7 degrees above absolute zero. That is minus 266 degrees Celsius. This temperature is so extreme that it cannot be reached even with the passive cooling of the massive sunshield. That's why MIRI has its own active cooler, a kind of state-of-the-art refrigerator that works in space. This cryo-cooler makes MIRI one of the coldest detectors in the universe. And thanks to this extreme cold, MIRI is so sensitive that it could theoretically detect the heat signature of a single bumblebee on the surface of the Moon. This is the power that revealed the ghost galaxy, ASTEF 71, which was completely invisible to Hubble. However, one of the telescope's most important instruments was not actually an instrument at all. It was space itself. Because Webb uses a trick that Albert Einstein taught it more than a century ago. Einstein's general theory of relativity states that mass bends space-time, just as a heavy bowling ball placed on a stretched sheet bends the sheet downwards. As light passes through this curved space, its path is also bent. This effect is called gravitational lensing. For astronomers, this is a natural magnifying glass that the universe offers them for free. Because when Webb looks at a very massive galaxy cluster in the foreground, the immense mass of that cluster magnifies and focuses the light from even more distant objects located directly behind it. This way, even galaxies that would normally be too faint to see become visible. Webb's first famous deep field image, the galaxy cluster SMACS 0723, used exactly this technique. Those strange, elongated and arc-shaped galaxies in the image are actually normally shaped galaxies, but their light has been distorted and magnified by the gravitational lens of the cluster in front of them. Without this lensing effect, it would have been impossible to detect some of the most distant and faintest galaxies. ESO, when you combine Webb's incredible sensitivity with the natural magnifying power of gravitational lenses, you get a window into the earliest era of the universe. ESO, we have an incredible set of tools. A telescope that hides from the heat of the Earth and the Sunday, a giant gold-coated mirror designed to capture the faintest infrared light from the most distant corners of the cosmos, a spectrograph that splits this light into its chemical fingerprints, and a technique that uses the universe itself as a natural magnifying glass. All these systems work together to give us a picture of the early universe that is more detailed and profound than we could ever have imagined. But these technical details, these engineering marvels, are only part of the story. What's truly exciting is what these tools are showing us. Because Webb didn't just confirm old theories, it fundamentally shook some of them and forced us to rethink some of our most basic assumptions about the origins of the universe. And now comes the real miracle. Because Webb didn't just look at distant galaxies, it looked at the most fundamental building blocks of the universe, the first stars. And what it found there changed everything. Because this machine revealed things that not even its creators expected. Webb didn't just confirm old theories, it fundamentally shook some of them. This was the beginning of a series of discoveries that forced us to rethink our most basic assumptions about the origins of the universe. And some of the most shocking of these discoveries were not just about how big galaxies were, but also about how quickly the universe itself was structured. For decades, scientists had been searching for the first generation of stars. They were known as Population 3 stars. These stars were a legend. They were made of only hydrogen and helium, the pure raw material of the Big Bang. Without the cooling effect of heavy elements, they should have grown to enormous sizes. Monsters with masses of 100, or even 1,000 times that of the Sunday. These stars were supposed to shine extremely brightly, live very fast, and die very violently. But all these stars should have been long dead. Seeing them directly was considered impossible, until now, because when Webb looked into the deepest depths of the universe, it found not the first stars, but the chemical fingerprints left behind by their moments of death. The spectrographs detected clear signatures of oxygen, carbon, and magnesium in galaxies that were only 500 million years old. This was Im, Pos, Psi, Bel, because to produce these elements, at least one generation of giant stars had to have lived and exploded as supernovae. Webb's discoveries proved that this process happened hundreds of millions of years before models predicted. The universe was chemically enriched while it was still in its infancy. This discovery caused an earthquake in the scientific world, because it meant pushing forward the entire timeline of galaxy formation. Everything had happened much faster than we thought, but this was only the beginning. An even bigger shockwave was approaching, because the rapid death of the first stars had enriched the universe with heavy elements. So, what was the rate of this enrichment? This is where Webb revealed a second, deeper impossibility. Astronomers measured how abundant alpha elements, like oxygen and magnesium, were compared to iron. This ratio is a kind of clock for a galaxy's star formation history, because alpha elements are produced quickly in the supernova explosions of giant stars that live only a few million years. Iron, on the other hand, is produced more slowly through the explosions of smaller stars that live for billions of years. Therefore, a high alpha to iron ratio indicates that a galaxy formed most of its stars in a short, intense burst. And Webb found that the earliest galaxies carried this exact signature. These galaxies were not producing stars slowly and steadily. Like a cosmic fireworks show, they were experiencing a giant star formation burst, consuming all their gas reserves in just a few 100 million years. Some of these galaxies were producing hundreds, even thousands of new stars per year. Compare this to the Milky Way's current production of only 2 to 3 stars per year. This was an AB Solu-Telai incredible rate. This showed how violent and chaotic the early universe was. However, this was not the most shocking part of the discovery, because this rapid life also meant a rapid death, and here, Webb found something that stunned researchers: dead galaxies. Galaxies that had completely stopped active star formation when the universe was only 1 billion years old. This was an absolute paradox. These quenched galaxies had consumed their fuel so quickly and so early that they had completed their entire evolution billions of years before our own sun was born. They were cosmic fossils from a time that had barely begun. Imagine finding the ruins of an ancient civilization older than the invention of fire. It didn't fit. The universe was not only creating life in record time, it was also creating death in record time. Timelines were collapsing at every level. The scientific community was faced with a wreckage. Their models of a slow, calm universe were not just wrong, they were the exact opposite of the truth. And now we come to the real climax, to the monster at the center of it all. Scientists wondered what was hiding at the center of these early, hyperactive galaxies. The answer surpassed all expectations and definitively broke the laws of physics. Webb observed a quasar shining when the universe was only 700 million years old. Quasars are the brightest objects in the universe, and their light is emitted from the disks around actively feeding supermassive black holes. But when the mass of the black hole powering this quasar was calculated, scientists were shocked. Its mass was estimated to be several 100 million times that of the Sunday. Let's repeat that. A black hole of hundreds of millions of solar masses when the universe was only 700 million years old. This could not be explained by any known formation path. Even feeding beyond the Eddington limit was not enough to reach this size from a stellar remnant seed. There was no time. The math did not allow it. But it got worse. Webb broke one record after another. It continued to find black holes with masses exceeding 1 billion solar masses within the first billion years of the universe. 1 billion suns, in a universe less than 1 billion years old. Each new discovery widened the crack in the standard model a little more. The scientific world was watching the collapse of one of the most fundamental paradigms of cosmology, and in the midst of this crisis, Webb found one last piece of evidence from an unexpected place. From the expansion rate of the universe itself, a problem known as the Hubble tension had been plaguing physics for decades. The expansion rate calculated from early universe observations, the cosmic microwave background radiation, did not match the expansion rate obtained from direct measurements of the modern universe, from distant supernovae. There was a small but persistent difference between the two values. Many hoped it was due to measurement errors, but Webb entered this debate with its ability to measure distant distances with unprecedented precision, and Webb's data did not do what everyone had hoped. It did not solve the problem. It not only confirmed that this discrepancy was real, it exacerbated it. This was not a simple measurement error. This was a sign that we misunderstood a fundamental property of the universe. Perhaps dark energy was changing over time. Perhaps there was a new particle or a new force missing from our standard model. Whatever the answer, Webb's discoveries pushed cosmology into completely unknown territory. SO, we have accelerated chemical enrichment. We have violent star formation bursts. We have galaxies that died UN Bili Vibli early. We have impossibly large black holes, and we have a fundamental anomaly in the expansion of the universe. They all point in the same direction. The early universe was not the place we thought it was. It was faster, more violent, and much more efficient. Our standard model failed to describe the childhood of the universe. SO, what could take its place? What was the invisible hand that drove all these processes at such an impossible speed? So, scientists focused on one of the telescope's most fundamental tasks, mapping the invisible skeleton of the universe. Because behind all these visible structures, there was an invisible hand that formed the skeleton of everything, dark matter. And Webb's discoveries showed that even this invisible hand was behaving differently than we thought. Because dark matter does not emit light, it does not reflect light, but it has gravity, and there is about 5 times more dark matter in the universe than normal matter. According to the standard model, dark matter acts as a scaffold for normal matter. First, dark matter clumped into giant halos. Then, normal matter fell into these gravitational wells and formed the first stars and galaxies. This process was supposed to be slow and take hundreds of millions of years. However, the mature early galaxies found by Webb contradicted this story. Their existence meant that the dark matter skeleton must have been established much earlier and much faster than we thought. This was a fundamental problem, because the clumping speed of dark matter is determined by the fundamental parameters of the universe. Changing this speed means changing the entire evolution of the cosmos. Webb's data suggested that dark matter simulations might be fundamentally wrong. Perhaps dark matter was not the cold, slow-moving particle we thought it was. Perhaps it had interactions within itself that our models did not account for. This opened a door that questioned not only cosmology, but also the most fundamental principles of particle physics. Scientists saw that the dark matter theories they had built for decades were being shaken by the images sent back by Webb. But the most shocking thing Webb found about dark matter was the evidence that it might not be just a passive scaffold. It could be an active engine. Do you remember the dark stars theory we mentioned earlier? This theory was considered a highly speculative idea before Webb's data came in. But then Webb analysed the spectra of some of the most distant and brightest objects, and there it found strange signatures that did not fit the spectrum of a normal galaxy or quasar. 3 candidate objects were particularly noteworthy. They were incredibly bright for their redshifts. Their spectral features did not match standard models. However, they showed a surprisingly good fit with the theoretical spectral signature of a dark star. This was not definitive proof, but for the first time in history, there was a concrete, observable clue supporting this radical idea. If these objects were indeed dark stars, it would change everything. It would mean that dark matter was not just a passive scaffold, but an active fuel that directly powered some of the universe's first light sources. It would mean that stars could exist that reached 1 million solar masses, shining as brightly as an entire galaxy, and leaving a giant black hole seed at the end of their lives. The scientific world was divided. Some argued it was a statistical coincidence. Others thought they were witnessing the dawn of a new era in cosmology. And in the midst of this theoretical storm, Webb presented the clearest picture of the large-scale structure of the universe we have ever seen, the cosmic web. Galaxies are not randomly distributed in space. Like a spider's web, they are grouped into long, filamentary structures and dense nodes that surround giant voids. The structure of this web is shaped by the tiny density fluctuations left over from the Big Bang and the gravitational influence of dark matter. But, until now, it was impossible to see the earliest and faintest threads of this web. With its incredible sensitivity, Webb discovered a 3 million light-year-long filament connecting 10 galaxies at the center of a protocluster. And this protocluster existed when the universe was only 830 million years old. This was the oldest and most distant cosmic web filament ever observed. This discovery was important because it confirmed that the universe could form such large and organized structures at such an early stage, just as standard models predicted. But it also revealed a contradiction, because within this giant, expected structure, there were again those impossibly large and mature galaxies. This showed that the universe was behaving as expected on large scales, while completely exceeding expectations on the small scales of individual galaxy formation. It was a puzzle. Did physics change with scale, or was there a missing piece that could explain both the large-scale structure and the accelerated small-scale formation at the same time? All these discoveries, these impossibilities, these records lead us to one inevitable conclusion. Webb didn't just take a photograph of the universe, it showed us a movie where the first moments of the universe were more dynamic, violent, and creative than we could ever have imagined. In this movie, the heroes were not who we expected. Galaxies were not slow-growing babies, but giants that appeared suddenly. Black holes were not patient eaters, but insatiable monsters, and dark matter was not a silent architect, but perhaps the force that ignited the universe's first fire. Every image, every spectrum, invalidated a chapter in the textbooks. Every data packet shook theories that had stood for decades. This is not just the story of a telescope, this is the story of a fundamental shift in humanity's understanding of its place in the universe. But now, after this dizzying pace of discovery, it is time to pause for a moment and reflect. What do all these numbers, these explosions, and these impossible objects mean for us? For humanity? Because this new universe that Webb has shown us is not just questioning the models of astronomers, it is also questioning our deepest perceptions of our own existence. Who are we in such a vast, such an ancient, and such a strange universe? What is our place in the midst of all this cosmic drama? These questions don't just concern physics, they concern philosophy, meaning, and what it means to be human, because the deepest secrets of the universe are not only about physics, they are also about existence. And what Webb has shown us is that the foundation of our existence is far more chaotic and creative than we thought. Monsters with masses of 100, or even 1,000 times that of the Sunday, these stars were supposed to shine extremely brightly, live very fast, and die very violently. But all these stars should have been long dead. Seeing them directly was considered impossible, until now, because when Webb looked into the deepest depths of the universe, it found not the first stars, but the chemical fingerprints left behind by their moments of death. The spectrographs detected clear signatures of oxygen, carbon, and magnesium in galaxies that were only 500 million years old. This was Im, Pos, Psi, Bel, because to produce these elements, at least one generation of giant stars had to have lived and exploded as supernovae. Webb's discoveries proved that this process happened hundreds of millions of years before models predicted. The universe was chemically enriched while it was still in its infancy. This discovery caused an earthquake in the scientific world, because it meant pushing forward the entire timeline of galaxy formation. Everything had happened much faster than we thought. But this was only the beginning. An even bigger shockwave was approaching, because the rapid death of the first stars had enriched the universe with heavy elements. So, what was the rate of this enrichment? This is where Webb revealed a second, deeper impossibility. Astronomers measured how abundant alpha elements, like oxygen and magnesium, were compared to iron. This ratio is a kind of clock for a galaxy's star formation history. Because alpha elements are produced quickly in the supernova explosions of giant stars that live only a few million years. Iron, on the other hand, is produced more slowly through the explosions of smaller stars that live for billions of years. Therefore, a high alpha to iron ratio indicates that a galaxy formed most of its stars in a short, intense burst. And Webb found that the earliest galaxies carried this exact signature. These galaxies were not producing stars slowly and steadily. Like a cosmic fireworks show, they were experiencing a giant star formation burst, consuming all their gas reserves in just a few 100 million years. Some of these galaxies were producing hundreds, even thousands of new stars per year. Compare this to the Milky Way's current production of only 2 to 3 stars per year. This was an AB Solu-Telai incredible rate. This showed how violent and chaotic the early universe was. However, this was not the most shocking part of the discovery, because this rapid life also meant a rapid death. And here, Webb found something that stunned researchers: dead galaxies. Galaxies that had completely stopped active star formation when the universe was only 1 billion years old. This was an absolute paradox. These quenched galaxies had consumed their fuel so quickly and so early that they had completed their entire evolution billions of years before our own sun was born. They were cosmic fossils from a time that had barely begun. Imagine finding the ruins of an ancient civilization older than the invention of fire. It didn't fit. The universe was not only creating life in record time, it was also creating death in record time. Timelines were collapsing at every level. The scientific community was faced with a wreckage. Their models of a slow, calm universe were not just wrong, they were the exact opposite of the truth. And now we come to the real climax, to the monster at the center of it all. Scientists wondered what was hiding at the center of these early, hyperactive galaxies. The answer surpassed all expectations and definitively broke the laws of physics. Webb observed a quasar shining when the universe was only 700 million years old. Quasars are the brightest objects in the universe, and their light is emitted from the disks around actively feeding supermassive black holes. But when the mass of the black hole powering this quasar was calculated, scientists were shocked. Its mass was estimated to be several 100 million times that of the Sunday. Let's repeat that. A black hole of hundreds of millions of solar masses when the universe was only 700 million years old. This could not be explained by any known formation path. Even feeding beyond the Eddington limit was not enough to reach this size from a stellar remnant seed. There was no time. The math did not allow it. But it got worse. Webb broke one record after another. It continued to find black holes with masses exceeding 1 billion solar masses within the first billion years of the universe. 1 billion suns, in a universe less than 1 billion years old. Each new discovery widened the crack in the standard model a little more. The scientific world was watching the collapse of one of the most fundamental paradigms of cosmology. And in the midst of this crisis, Webb found one last piece of evidence from an unexpected place. From the expansion rate of the universe itself, a problem known as the Hubble tension had been plaguing physics for decades. The expansion rate calculated from early universe observations, the cosmic microwave background radiation, did not match the expansion rate obtained from direct measurements of the modern universe, from distant supernovae. There was a small but persistent difference between the two values. Many hoped it was due to measurement errors, but Webb entered this debate with its ability to measure distant distances with unprecedented precision, and Webb's data did not do what everyone had hoped. It did not solve the problem. It not only confirmed that this discrepancy was real, it exacerbated it. This was not a simple measurement error. This was a sign that we misunderstood a fundamental property of the universe. Perhaps dark energy was changing over time. Perhaps there was a new particle or a new force missing from our standard model. Whatever the answer, Webb's discoveries pushed cosmology into completely unknown territory. So, we have accelerated chemical enrichment. We have violent star formation bursts. We have galaxies that died UN-Bili Vibli early. We have impossibly large black holes. And we have a fundamental anomaly in the expansion of the universe. They all point in the same direction. The early universe was not the place we thought it was. It was faster, more violent, and much more efficient. Our standard model failed to describe the childhood of the universe. SO, what could take its place? What was the invisible hand that drove all these processes at such an impossible speed? So, scientists focused on one of the telescope's most fundamental tasks, mapping the invisible skeleton of the universe. Because behind all these visible structures, there was an invisible hand that formed the skeleton of everything, dark matter. And Webb's discoveries showed that even this invisible hand was behaving differently than we thought. Because dark matter does not emit light, it does not reflect light, but it has gravity, and there is about 5 times more dark matter in the universe than normal matter. According to the Standard Model, dark matter acts as a scaffold for normal matter. First, dark matter clumped into giant halos. Then, normal matter fell into these gravitational wells and formed the first stars and galaxies. This process was supposed to be slow and take hundreds of millions of years. However, the mature early galaxies found by Webb contradicted this story. Their existence meant that the dark matter skeleton must have been established much earlier and much faster than we thought. This was a fundamental problem, because the clumping speed of dark matter is determined by the fundamental parameters of the universe. Changing this speed means changing the entire evolution of the cosmos. Webb's data suggested that dark matter simulations might be fundamentally wrong. Perhaps dark matter was not the cold, slow-moving particle we thought it was. Perhaps it had interactions within itself that our models did not account for. This opened a door that questioned not only cosmology, but also the most fundamental principles of particle physics. Scientists saw that the dark matter theories they had built for decades were being shaken by the images sent back by Webb. But the most shocking thing Webb found about dark matter was the evidence that it might not be just a passive scaffold. It could be an active engine. Do you remember the dark stars theory we mentioned earlier? This theory was considered a highly speculative idea before Webb's data came in. But then Webb analysed the spectra of some of the most distant and brightest objects, and there it found strange signatures that did not fit the spectrum of a normal galaxy or quasar. 3 candidate objects were particularly noteworthy. They were incredibly bright for their redshifts. Their spectral features did not match standard models. However, they showed a surprisingly good fit with the theoretical spectral signature of a dark star. This was not definitive proof, but for the first time in history, there was a concrete, observable clue supporting this radical idea. If these objects were indeed dark stars, it would change everything. It would mean that dark matter was not just a passive scaffold, but an active fuel that directly powered some of the universe's first light sources. It would mean that stars could exist that reached 1 million solar masses, shining as brightly as an entire galaxy, and leaving a giant black hole seed at the end of their lives. The scientific world was divided. Some argued it was a statistical coincidence. Others thought they were witnessing the dawn of a new era in cosmology. And in the midst of this theoretical storm, Webb presented the clearest picture of the large-scale structure of the universe we have ever seen, the cosmic web. Galaxies are not randomly distributed in space. Like a spider's web, they are grouped into long, filamentary structures and dense nodes that surround giant voids. The structure of this web is shaped by the tiny density fluctuations left over from the Big Bang and the gravitational influence of dark matter. But, until now, it was impossible to see the earliest and faintest threads of this web. With its incredible sensitivity, Webb discovered a 3 million light-year-long filament connecting 10 galaxies at the center of a protocluster, and this protocluster existed when the universe was only 830 million years old. This was the oldest and most distant cosmic web filament ever observed. This discovery was important because it confirmed that the universe could form such large and organized structures at such an early stage, just as standard models predicted. But it also revealed a contradiction, because within this giant, expected structure, there were again those impossibly large and mature galaxies. This showed that the universe was behaving as expected on large scales, while completely exceeding expectations on the small scales of individual galaxy formation. It was a puzzle. Did physics change with scale, or was there a missing piece that could explain both the large-scale structure and the accelerated small-scale formation at the same time? All these discoveries, these impossibilities, these records lead us to one inevitable conclusion. Webb didn't just take a photograph of the universe, it showed us a movie where the first moments of the universe were more dynamic, violent, and creative than we could ever have imagined. In this movie, the heroes were not who we expected. Galaxies were not slow-growing babies, but giants that appeared suddenly. Black holes were not patient eaters, but insatiable monsters, and dark matter was not a silent architect, but perhaps the force that ignited the universe's first fire. Every image, every spectrum, invalidated a chapter in the textbooks. Every data packet shook theories that had stood for decades. This is not just the story of a telescope, this is the story of a fundamental shift in humanity's understanding of its place in the universe. But now, after this dizzying pace of discovery, it is time to pause for a moment and reflect. What do all these numbers, these explosions, and these impossible objects mean for us? For humanity? Because this new universe that Webb has shown us is not just questioning the models of astronomers, it is also questioning our deepest perceptions of our own existence. Who are we in such a vast, such an ancient, and such a strange universe? What is our place in the midst of all this cosmic drama? These questions don't just concern physics, they concern philosophy, meaning, and what it means to be human. Because the deepest secrets of the universe are not only about physics, they are also about existence. And what Webb has shown us is that the foundation of our existence is far more chaotic and creative than we thought. The first, and perhaps most staggering truth Webb presents us with, is this overwhelming paradox of scale. On one hand, there is the observable universe, with an estimated radius of 46 billion light-years. It is estimated to contain 2 trillion galaxies, and each of these galaxies contains hundreds of billions of stars. These numbers are so enormous that the human mind cannot truly comprehend them. We are on a small, wet rock orbiting an ordinary star, in a suburb of a single galaxy, in this unimaginably vast cosmic ocean. On the other hand, there is our effort to understand this universe. A machine, not much larger than a tennis court, built by us, 1.5 million kilometers away. This machine captures light that set out 13.5 billion years ago and analyzes the finest details within that light. How can these two scales coexist? This is perhaps the greatest and most poignant truth of the universe. Because this overwhelming size confronts us with our absolute physical limitations. We will never travel to those galaxies. We will never touch those ancient stars. We can only see them as faint points of light from an impassable distance. This is like standing on the shore of an ocean, knowing you can never experience the lives happening on the opposite shore. Physically, we are overwhelmingly lonely and insignificant inhabitants of this universe. But then comes that glorious but moment. Because we can understand that light, we may not be able to go there, but with our minds, our mathematics, and our engineering, we can cross that infinite distance. We can precisely measure the amount of iron, oxygen, and carbon in that tiny, faint point of light. We can calculate how fast that galaxy is rotating, how many stars it is producing, and how big the black hole at its center is. We may be physically small and trapped, but our ability to understand is as vast and limitless as the universe itself. You live in the very middle of this paradox. Every morning you wake up, your feet are firmly on the ground of this planet. But your mind can reach for the stars. Your body is chained to this tiny rock, but your imagination can travel freely among the galaxies. Webb is the most concrete example of this human condition. It is a monument to the incredible and persistent desire of a physically tiny being to understand the greatest secrets of the universe. And this leads us directly to a second, equally profound contrast, the paradox of time. The universe is 13.8 billion years old. This is such a long period of time that an entire human lifetime is less than a single blink of an eye next to it. If the entire history of the universe were compressed into a single calendar year, all of recorded human history would fit into the last few seconds before midnight, on the night of December 31st. Your life and mine are a millisecond within that final second. We are fleeting sparks in this vast ocean of time. The galaxies Webb shows us were born, lived, and died billions of years before we existed. Their light set out towards us, before Earth had even become a planet. We are extras who appear on stage in the final scene of this cosmic film. This is perhaps the most tragic truth of our existence, our transience. No matter how hard we try, we are nothing more than a tiny ripple in this cosmic river of time, caught between the eternity before us and the eternity after us. But, there comes that wonderful word "but" again, because we can see the entire river. We may be temporary, but through our consciousness, we can step out of our tiny moment in time and look back at its beginning. Webb is our time machine. It shows us the depths not only of space, but of time. We can witness the birth of the first galaxies, the death of the first stars, and the evolution of the universe itself. We can witness a reality that existed billions of years before our own existence. Our own existence may be fleeting, but through our ability to understand, we can recreate the entire 13.8 billion year history of the universe in our minds. You are a part of this fleeting yet infinitely meaningful existence. Your life is short. Yes, but in this short time, you have the chance to look at the beginning of the universe, to question your own origins, and to understand that you are part of a much, much larger story. This is not a tragedy of transience. This is a privilege, and this brings us to one last contrast for now, the delicate balance between loneliness and connection. The universe Webb shows us is incredibly empty. The distances between galaxies are immense, voids that even light takes millions of years to cross. Each galaxy seems to be its own island universe, separated from the others by a deep, dark ocean. This creates a sense of cosmic loneliness. Even if there are other intelligent life forms out there somewhere, in one of those distant galaxies, communicating with them is nearly impossible due to the laws of physics. We seem to be trapped in our small cosmic neighborhood. This is perhaps the saddest truth of the universe. A cosmos full of potential knowledge, but we are condemned to be potentially completely alone. But, that magical word comes again, but. Yet, we are made of the same matter as those galaxies. The iron in your blood was forged in the heart of a star that died in a giant supernova billions of years ago. The oxygen you are breathing right now was launched into space by another stellar explosion. The calcium in your bones is a product of generations of stellar life and death. We are stardust. This is not a poetic expression. It is a scientific fact. When Webb found iron and oxygen in those earliest galaxies, it actually found the oldest branches of our own family tree. Those galaxies are not separate from us. They are our ancestors. Their story is our story. We are physically separate, but we are chemically, inextricably linked. You are living proof of this cosmic bond. Every single atom in your body was created in a different corner of the universe, at a different time, inside a star. You are a being formed by the union of pieces from all over the cosmos. This is the opposite of loneliness. This is connection in the deepest sense. These three paradoxes, scale, time, and connection, are the deepest lessons Webb has taught us. They don't just show us how big, old, and strange the universe is. They also show us how special and meaningful our place in this universe is. But this is only the beginning. Because beyond these reflections, Webb's discoveries also ask profound questions about the future and our ultimate destiny. And this brings us to perhaps the most human paradox, the paradox of knowledge and mystery. The Webb telescope is the most powerful information-gathering tool in human history. It has taught us more about the universe than we could have imagined just a decade ago. We now know when the first galaxies formed. We know how big the first black holes were. We know how truly fast the chemical evolution of the universe was. Our knowledge has increased exponentially. The map of the universe is more detailed than ever. This is an absolute triumph of human intellect and our relentless curiosity. We are a species that does not run from the unknown, but stubbornly tries to understand it. But there is that inevitable and humbling but moment again, because every new piece of knowledge we gain, every equation we solve, shows us even more clearly how infinitely little we actually know. When Webb answered one question, it created 10 new, deeper questions. We found impossible galaxies, but now we have to explain how they could form so quickly. We found giant black holes, but now we have to find out where their monster seeds came from. We even found possible evidence for dark stars, but now we have to prove whether they actually exist. As our horizon of knowledge expands, the ocean of mystery beyond that horizon also grows. This is perhaps the most tragic, and at the same time, the most beautiful truth of science. We will never reach the final answer. There will always be a new continent to discover, a new puzzle to solve. Our quest for knowledge is endless. But this is not a bug in the system. It is a gift, because this infinite mystery is the engine that pushes us forward. It is what forces us to build new telescopes, to develop new theories, and to always look deeper. You are a part of this endless quest. Everything you learn in your life may be just a drop in the ocean of knowledge, but that drop tells you something about the ocean itself. And every new drop helps you understand even better how vast, how deep, and how wonderful that ocean is. Perhaps the greatest lesson Webb has taught us is precisely this. It is not the answers that are most important, but the questions. Because questions keep our curiosity alive. And curiosity is the essence of being human. This curiosity inevitably leads us to the biggest question: are we alone? Webb was not designed to answer this question directly, but every discovery it makes puts another piece of the puzzle in place that shapes the ultimate answer to this question. On one hand, the universe Webb shows us seems to be a potentially much more hospitable place for life than we ever thought possible, because we have learned that the early universe was chemically enriched much faster than we thought. The building blocks of life as we know it, carbon, oxygen, iron, were abundant very early in the universe. This means that rocky planets, potentially habitable worlds, could have started forming billions of years earlier than thought. The universe had much more time and many more opportunities to prepare the chemical ingredients for life to emerge. This is an extremely hopeful thought, but on the other hand, the universe Webb shows us was also an incredibly violent and chaotic place. Gamma-ray bursts that would sterilize any nearby life, supernova explosions of giant stars, the intense, deadly radiation of actively feeding supermassive black holes. The early universe was not a safe harbor for delicate life forms to emerge. This is a deep paradox. That the very processes absolutely necessary for life, the death of stars and the production of heavy elements, are also the most violent and destructive events that can destroy life. This is a tragic irony of the universe. The seeds of life are sown in the midst of the cosmos's deadliest storms. You are a direct product of this paradox. Your existence is the result of this billions of years long cycle of cosmic violence and creativity. For you to exist, countless stars had to be born, live, and die in massive explosions. You are an heir to this dangerous but infinitely fertile universe. Webb reminds us how fragile and how infinitely precious our place in the universe is. How do you feel when you are confronted with all this information? On one hand, perhaps a deep sense of awe and even a slight fear in the face of the universe's overwhelming vastness and our apparent insignificance. On the other hand, perhaps a deep sense of pride and wonder at our incredible ability to understand this universe and find our place within it. Both are correct, both are valid, because what Webb really shows us is that these two feelings do not contradict each other. They can coexist. We are both insignificant and infinitely precious. We are both lost in the cosmos and at the center of the universe. Because the center of the universe is not a place, it is a point of view. And in this moment, as you watch and think, that center is you. The greatest gift this telescope has given us is this new perspective. It takes us from our daily worries and places us inside a much, much larger story. It reminds us that we are all made of the same stardust and are all floating in the same cosmic ocean. So we have seen how vast, how ancient, and how strange the universe is. And we have understood how paradoxical, but also how meaningful our place in this universe is. Scale, time, connection, knowledge, and life. They are all philosophical tensions that form the basis of the human condition. We now know that the history of the universe is our history, and our history is an inseparable part of the history of the universe. But there is perhaps one more important question. What do we do with all this knowledge? And so now, we face perhaps the most internal and most challenging question. What should we do with all this cosmic knowledge, with this new and strange portrait of the universe? This is no longer just a scientific question. It is a deeply personal one, because this knowledge inevitably changes us. It fundamentally reshapes our view of the world and ourselves. This new reality that Webb presents to us confronts us with new and deeper paradoxes, not just about our place in the universe, but about our actions and our meaning within it. And the first of these paradoxes is the deep chasm between understanding and action. Thanks to Webb and decades of research, we have an almost unbelievable understanding of the fundamental workings of the universe. Our theories, like general relativity and quantum mechanics, allow us to describe the universe on the largest and smallest scales with astonishing precision. We can analyze the chemical signature of a gamma-ray burst that occurred 13 billion years ago. We can map the invisible structure of dark matter that forms the skeleton of the cosmos. We can detect that tiny but meaningful discrepancy in the expansion rate of the universe. Our ability to understand is perhaps our species' greatest achievement. It is our superpower. But there is that inevitable and deeply humbling but moment again. We are completely powerless in the face of these vast universal processes. We understand them, but we cannot control them in the slightest. We can predict when a supernova will explode in our cosmic neighborhood, but we cannot stop it. We know how dark energy is unstoppably tearing the universe apart, but we cannot reverse this process. We know that our galaxy will inevitably collide with the Andromeda galaxy in a few billion years, but we cannot cancel this cosmic appointment. This is perhaps the most tragic aspect of knowledge. We are beings who can read the rules of the universe, but can never change those rules. Like an old sailor who can read the signs in the sky and understand the coming of a giant storm but cannot stop it. We can only stand on the deck and witness this overwhelming power of nature. However, and this however, changes everything. Understanding itself is an action. We may not be able to change the universe, but this knowledge can and will change us. This knowledge teaches us humility. It reminds us how small and how fragile we are. But it also gives us an invaluable perspective. The small worries and conflicts of our daily lives become meaningless in the face of cosmic events like the collision of galaxies or the death of stars. This knowledge can make us wiser, more patient, and perhaps more compassionate towards other people. You are also within this paradox. There are many things in your life you cannot control, but you have the power to understand them and to choose how you react to them. What Webb teaches us is not to control the universe, but to understand it and to find our own place within that understanding. And this leads us to another, even deeper contrast, the contrast between individuality and universality. You are one of 8 billion people on this planet. You have a unique consciousness, unique memories, hopes, and fears. The personal story that runs through your mind will never be repeated in the entire universe. In this sense, you are completely individual and ultimately alone. You look at the world through the unique prism of your own experiences, trapped in your own mind. This is a fundamental truth of human existence. We are born alone and we die alone. This might seem like the most fundamental tragedy of existence. We are forever trapped within the confines of our own consciousness. But the universe that Webb shows us fundamentally shatters this perception, because it also reminds us how infinitely universal we are, because the atoms that make you up were not just forged inside a star that died billions of years ago. They are the same atoms that make up every single person, every single animal, and every single plant on this planet. We all come from the same cosmic source, but it goes deeper. The physical laws that govern you, from the chemical reactions in the cells of your body to the electrical signals that fire the neurons in your brain, are the same laws that were set in the Big Bang 13.8 billion years ago. These laws also apply to a star in the most distant galaxy. These laws also govern the collision of two black holes. This is the deepest bond that unites us all. We may be separated by our individual consciousness, but at the core of our physical existence, we are all woven from the same fabric of the universe. You are an expression of the universe itself. Your body is a summary of the universe's 13.8 billion year history, and your consciousness is one of the ways the universe knows and questions itself. This is the opposite of loneliness. You are both a unique individual and an inseparable part of a universal whole. And this sense of connection leads us to one final paradox: the delicate dance between meaninglessness and meaning. From a purely scientific perspective, there is no inherent purpose or meaning in the universe. The universe simply is. It operates according to the laws of physics. The Big Bang did not happen for a specific reason. Galaxies did not form for a specific reason. Stars did not die as part of a grander plan. This is a cold and indifferent universe. Our existence is the random result of a chain of coincidental events spanning billions of years. This can be a disturbing and cold thought for some. It can be difficult to accept that our lives are not part of a grander cosmic plan. This might seem like the most tragic aspect of existence, to be beings desperately searching for meaning in a universe that is inherently meaningless and purposeless. However, and this is perhaps one of the most important howevers, the universe may not give us meaning, but we can give meaning to the universe. Consciousness itself is the most meaningful phenomenon in the universe, because consciousness is the ability to create meaning. The Webb telescope itself is the most beautiful example of this. It is just a machine made of metal, glass, and electronics. It has no meaning on its own, but we gave it a purpose: to explore the universe. And when we look through that telescope, it is we who give meaning to those meaningless photons and those random distributions of galaxies. We turn them into patterns, we create stories, and we develop theories. We are the storytellers who tell the universe's own story. Meaning is not something found in the universe. It is something we create. You do this every day. You give meaning to the events, relationships, and experiences in your life. You are a meaning creation machine, and this ability is the greatest gift the universe has given you. We understand, but we are powerless. We are individual, but we are universal. We create meaning in a meaningless universe. However, at the end of this inner journey, another truth awaits us. A truth that perhaps reflects the fate of the telescope itself, and its story may be whispering to us that even the greatest adventures have an end. And this invites us to confront one last set of paradoxes, perhaps the most human of all, the inevitable cycle of creation and destruction, of end and beginning, because the story of the James Webb Space Telescope is a metaphor for our own existence. It is a product of human genius, a triumph of our creativity. It was created by the decades-long tireless work of tens of thousands of scientists and engineers. Every part, every cable, every line of code is a testament to human curiosity and our irrepressible will to understand the unknown. With the materials we took from the universe itself, we built an eye to search for meaning in the universe. This is the ultimate act of creation. However, there is that inevitable, humbling truth again. The Webb telescope has a limited lifespan. The fuel it uses to maintain its perfect orbit at the Lagrange point 2 will one day run out. On that day, it will become uncontrollable. Its mission will end. It will technically still be working, still cold and intact, but it will no longer be able to send new data to Earth. It will drift silently and alone in its orbit around the Sun, 1.5 million kilometers away from us, forever unreachable. We cannot bring it back. We cannot save it. It will become one of humanity's most advanced and loneliest monuments in space, a silent witness to our former curiosity. This is perhaps the most tragic truth of creation. Everything we create, no matter how magnificent, is ultimately destined to perish in the face of time and entropy. Nothing lasts forever, neither we nor our greatest works. But, that hopeful but, comes to our aid once more, because although the telescope may cease to exist as a physical object, the data it sent and the knowledge it gifted us will remain. This data will continue to be studied by future generations of scientists for decades, perhaps even centuries. From this data, new discoveries that we cannot even imagine today will be born. The next generation of scientists will build their own even greater discoveries upon Webb's priceless legacy. The physical existence of the created may end, but the knowledge and inspiration it created can live on forever, passed from mind to mind. You are also a part of this cycle. Throughout your life, you create things: relationships, ideas, works, memories. All of these, like yourself, are temporary. But the impact you leave behind, The lives you touch, the knowledge you share, can live on long after you are gone. And this leads us to a final profound contrast. The contrast between the end and the beginning. Webb's mission will one day end. This is an end, the closing of a glorious chapter in the history of human exploration. But it is also the beginning of something new, because the questions Webb has asked us are much larger than it can answer itself. By showing us how strange and wonderful the universe is, it has actually paved the way for the telescopes that will come after it. Scientists around the world are already planning the next generation of observatories that will take Webb's discoveries even further. The Nancy Grace Roman Space Telescope, unlike Webb's deep but narrow view, will survey vast areas of the universe to solve the mysteries of dark energy. The extremely large telescope on the ground, with a mirror that will dwarf Webb's, will be able to resolve individual star-forming regions in the earliest galaxies that Webb sees only as tiny dots. And perhaps one day, the Habitable Worlds Observatory will search for the chemical traces of life in the atmospheres of Earth-like planets around nearby stars. Every end sows the seed of a new beginning. This is the most fundamental law of the universe. Stars die, but from their ashes, new stars and planets are born. Galaxies collide and seem to be destroyed, but from these massive mergers, larger, richer, and more complex galaxies emerge. This is the most tragic, yet also the most hopeful truth of science. Every time we think we have found answers, we realize we have only found a door opening into a new, larger room full of even bigger and deeper questions. Our quest for knowledge never ends, because the universe itself is an infinite beginning. You also face many ends in your life. A job ends, a relationship ends, a phase of life closes. These ends can be painful, but they always carry within them the possibility of a new, unknown beginning. Webb's story teaches us that ends are not things to be feared. They are a natural and necessary part of evolution, growth, and new discoveries. At the end of this long internal journey, we find ourselves back at the starting point. A machine, 1.5 million kilometers away, looking into the deepest depths of the universe. And here on Earth, us, looking at the light sent by that machine, trying to understand not only the universe, but ourselves. What has this journey taught us? It has taught us that the universe is faster, more violent, and more creative than we could ever have imagined. It has revealed the paradoxes of our own existence, our smallness and our greatness, our transience and our reach, our loneliness and our connection. And it has taught us that even in the deepest darkness and emptiness, we can find meaning and connection, because we are not just made of stardust, we are also made of the curiosity and dreams that reach for the stars. Webb didn't just offer us a picture of the universe, it held up a mirror, and in that mirror, we saw our own curiosity, our own creativity, and our unwavering desire to understand even the greatest secrets of the universe. In this journey, we saw how the old, comforting story of a slow universe collapsed, and in its place came a new, violent, and creative reality. We met impossible galaxies, monster black holes, and the ghosts of invisible star factories. We understood that the laws of physics operate in ways that surpass our wildest dreams. We know now that the history of the universe is not a slow and predictable progression, but a drama filled with sudden leaps, unexpected turns, and seemingly impossible events. We know now that our existence is not an inevitable outcome of this cosmic drama, but an incredible product of a chain of happy accidents spanning billions of years. And we know now that our place in this universe is not that of a passive observer, but that of an active participant, trying to understand the universe and give it meaning. You are a part of this incredible story. Your consciousness is one of the rare places in the cosmos where the universe reflects upon itself. Within you live the echoes of the first stars and the curiosity that always pushes us to ask for more. If this journey has reminded you how wonderful, mysterious, and deep our cosmos is, then leave us a like and subscribe to the channel to be a part of future discoveries. Because within everything we have learned about the beginning, one final secret is hidden. The ultimate fate of the universe was perhaps already written in its first moments. In this journey, we have seen the surprising beginning of the universe. But I did not tell you a secret. The beginning itself contains the end. Will the universe cool and freeze forever? Or will it be torn apart until every atom is disintegrated? Or will it collapse back into the singularity where it all began? In our next journey, we will investigate the ultimate fate of the universe. The answers are hidden in those first moments that Webb found. Are you ready